Welcome back to the second part of Lecture 2 of our course, Introduction to Complex and Algebraic Geometry. So in the previous part, we learned about complex derivative and complex differentiable functions. So let's do a quick review. We discussed when a function f from C to C, or a function f where its domain is an open subset of C, is complex differentiable, right? We say it's complex differentiable at a point z if this limit exists. If f prime of z defined via this limit of f of z plus h minus f of z over h, where h goes to 0, if this limit exists, we would say f is complex differentiable at z. And if it's complex differentiable at any z in its domain, we would say f is complex differentiable, right? The other thing we learned is that being complex differentiable is very restrictive. Although it really looks like being real differentiable, the limit definition really is similar to the differentiability in calculus for real valued functions. This is really different, right? So we said being complex differentiable is quite restrictive, is a very hard property to have. So as an example, we learned polynomials. Polynomials in Z are complex differentiable. So we saw, for instance, f of z equals z squared is complex differentiable and its derivative is 2z as one would expect. However, we saw another example of a function that looks differentiable with the lens of real numbers, but as a complex valued function is not. So if we write z as x plus iy, we learned that f of z being defined by x plus y as its real part plus I x minus y, we learned this function actually is not complex differentiable. And we learned this has to do with the fact that here the variable h can go to 0 along any path in the complex plane. So unlike the case of real numbers where we have a one-dimensional line, real one-dimensional object, and there's just essentially one way to go to 0, well, maybe two ways, either from right or left. Here, our h, our complex variable, can go to 0 along any path, and that's why it's quite non-trivial compared to the calculus intuition. So this function, we learned this function does not have this limit. This limit does not exist for this function. So if you didn't see part 1, go and check that out. That's essential. Now, our big picture, what we are going to do is that we are going to see 3 perspectives on complex derivative or being complex differentiable. So one is this notion of being complex differentiable using this limit definition. The other thing we are going to learn today in this lecture is being holomorphic. This is related to something called Cauchy-Riemann equations. And we are going to see that these 2 notions are equivalent. And in the next part of this lecture, we are going to learn about analytic functions, which is a different way of thinking about complex differentiability. And we are going to see being analytic and holomorphic, they are also equivalent, which, I mean, that would imply complex differentiable and analytic are also the same. So this is our kind of big picture to have in mind. We learned about this. Today, we are going to learn about this and see why these 2 things are equivalent, right? Okay, so what does it mean to be holomorphic? So we have, let's say, a function from C to C or a subset of C to C, right? And C is essentially like R2. So both domain and target, they are very similar to R2. They're the same as a group, right? Also, z, any point in the domain, so any point z in the domain can be written as x plus iy. F of z would be in the target, so f of z would be something here. It is also a complex valued thing. So it also has a real part plus I imaginary part. So I can write it as u plus iv, where this is the real part of f, and this is the imaginary part of f. right? So we can write our complex valued function as its real part plus I imaginary part. We can do this with any complex valued functions. Right. So U and V, each of them, they are real valued, right? The real part and imaginary part both they take value in R. So U takes values in take value in R, V take values in R, right? So it's kind of like U takes X and Y. You can think about U as a function which takes X and Y, and the result would be in R. Same for V, right? So with this picture, U and V are two functions from R2 to R, or a subset of R2 to R. So U and V are two functions defined on R2 or a subset of R2. I'm just being lazy. I wrote R2 to R, right? The point is that now we want to see what would be the translation of F being complex differentiable for U and V. What does it mean for U and V? What property U and V should satisfy? So F would be complex differentiable, knowing F is equal to U plus IV. So this would be a property. We are looking for a property for U and V so that it would be equivalent to F being complex differentiable. And that is what is known as Cauchy-Riemann equations. So I'm going to write down the Cauchy-Riemann equations, and then I'm going to state the theorem. So definition, suppose U and V are two functions on R2 or an open subset of R2 to R. We would say U and V satisfy the Cauchy-Riemann equations. Cauchy and Riemann were two great mathematicians. They did a lot about complex analysis, complex geometry. Or more generally about analysis and geometry. The study of complex differentiability and these equations is part of their achievements. So they satisfy the Cauchy-Riemann equations if we have the following. So U and V are their functions on R2, so they have two variables, X and Y. So if derivative of U with respect to X, partial derivative of U with respect to X is equal to partial derivative of V with respect to Y, and partial derivative of U with respect to Y is equal to negative partial derivative of V with respect to X. So if U and V satisfy these equations are called the Cauchy-Riemann equations, right? We usually just use CR. Okay, so let's just look at an example. Let's say f of z is equal to z squared. So z is equal to x plus iy, and x plus iy squared is equal to x squared minus y squared plus I times 2xy. So here, u of x and y is the real part, which is x squared minus y squared. And v, which is the imaginary part, is equal to 2xy. So now we are going to check if this function satisfies these functions, they satisfy the Cauchy-Riemann equations. So what is derivative of u with respect to x? Well, we should take derivative of this function with respect to x. This is equal to 2x. What is derivative of v with respect to y? So we should take derivative of this function with respect to y. So just to remind you, when I'm taking derivative with respect to x, I assume y is a constant. When I take derivative with respect to y, I assume x is a constant. So here, I'm taking derivative with respect to y, so x is just like a constant. So 2x is like the constant coefficient of y, right? So when I take derivative with respect to y, derivative would be its coefficient, which is 2x. And you see these two are equal. Derivative of u with respect to x is equal to derivative of v with respect to y. What is derivative of u with respect to y? Well, now I should assume x is constant, so its derivative of x squared would be 0. Derivative of minus y squared would be minus 2y. And then I should take derivative of v with respect to x. What is derivative of v with respect to x? This is v. Again, I'm taking derivative with respect to x. So y should be like a constant. So 2y is the coefficient of x. And when I take derivative with respect to x, derivative would be its coefficient, which is 2y. And then the Cauchy-Riemann equation says derivative of u with respect to y should be equal to minus derivative of with respect to x. Well, 2y is equal to minus 2y times minus 1. So they do satisfy. So this is equal to minus derivative of v with respect to x. Definition. So this is the essential definition of this section. You say a function f defined on a subset of C to C is holomorphic. This is our definition for a function being holomorphic. If you write f as u plus iv, where u and v are two real valued functions, then the partial derivatives, derivative of u with respect to x, derivative of v with respect to x, derivative of u with respect to y, derivative of v with respect to y, they all exist and they're continuous. That's our definition. And they satisfy the Cauchy-Riemann equations. They satisfy the Cauchy-Riemann equations in the sense that derivative of u with respect to x, this is a more concrete way of writing it, equals derivative of v with respect to y, and derivative of u with respect to y equals minus derivative of v with respect to x. If we have that, we say f is holomorphic. Okay? Now, what is the theorem? Theorem is being complex differentiable, almost. Being complex differentiable and being holomorphic, they're equivalent. So let's do one way. We want to say being complex, f being complex differentiable is the same as f being holomorphic. Let's first prove one direction. Let's try to show complex differentiability implies holomorphicity. So let's say theorem. Suppose f is complex differentiable. So this means the limits we introduced exist, right? Then f is holomorphic. Okay, this is what we like to do. So I'm not going to present a detailed proof, but the proof is kind of simple. I'm going to just write the essential bit. So we are writing f as u plus iv, right? And we know, because f is complex differentiable, we know this limit exists. So we know f prime of z exists. We know this limit of f of z plus h minus f of z over h when h goes to 0. We know this limit exists. This is our assumption. We are assuming f is complex differentiable. So the main point, as we mentioned earlier, is that h can go to 0 along any path in the complex plane, right? H can be any complex variable, and we write it as h1 plus I h2, where h1 and h2 are real numbers. And this complex variable h going to 0 means its real part and its imaginary part, they also go to 0. So h1 and h2 also go to 0. And no matter how they go to 0, the value of this limit should be the same thing. That's the key thing, right? Okay, great. Now let's rewrite the limit. So f prime of z exists no matter how h1 and h2 go to 0. One way that h can go to 0 is when h1 goes to 0 as a variable, but h2 is equal to 0. So this is one way that h can go to 0. This is going to 0 along the real axis, right? So in this case, where our f is u plus iv, so h1 goes to 0, h2 is equal to 0, f is u plus iv, so it's u of x plus h1, y plus h2, but h2 is 0, plus iv at z plus h, which is x plus h1, and y plus 0, minus f of z, which is minus u of x and y, minus I vx and y, right? And we're dividing that by h, which is h1 plus I h2, which is 0, right? Okay, now we can break this into essentially two parts. So there is one part which is ux plus h1, y minus u of x and y divided by h1. There is this part. And then there is v of x plus h1 y minus v of x and y, the whole thing multiplied by I over h1. So this should these limits should exist when h1 goes to 0, right? But what is the first part? So just look at this bit. This is partial derivative of u with respect to x when h1 goes to 0 with the limit. Plus I, what is this thing? What is this limit when h1 goes to 0? This is partial derivative of v with respect to x. So if this function is complex differentiable, we should have f prime of z being equal to this thing. So these limits should exist, and f prime of z should be equal to this, this combination of partial derivatives. I leave some analysis details to you, but that's the bottom line. That's what we have. Okay. Now, let's do a different way of computing this limit. Suppose we are computing this limit f prime of z equal f of z plus h minus f of z over h, and then take limit and h go to 0. But this time, well, I would write h as h1 plus ih2, and we take the limit along the imaginary axis. So we let h1 to be equal to 0 and h2 a complex variable that is converging to 0 but not equal to 0. So this time f prime of z would be equal to this limit where h2 goes to 0. F is again u plus iv at the point x and y plus h. So here x plus h1, but h1 is 0. Y plus h2 plus iv, x, y plus h2 minus f of z. So it's minus u of x and y minus iv of x and y over h1 plus ih2. But h1 again is 0, so it's just ih2. So it's 0 plus ih2, right? And again, we break this into two parts. So there is u of x and y plus h2 minus u of x and y over ih2. And then there is v of x and y plus h2 minus iv of x and y over ih2, right? Okay, great. So what is this? What is the value of each of these limits? So if we ignore I here in the denominator and just take a limit of this part, this would be the partial derivative of u with respect to y. We're taking partial derivative with respect to y divided by I. So there is 1 over I here, but 1 over I is equal to minus I, right? Here we can cancel I. What remains is partial derivative of v with respect to y. So f prime of z should be equal to this combination of partial derivatives. But previously, in the previous page, we had a different value for f prime. We had this partial derivative of u with respect to x plus I partial derivative of v with respect to x. So if this limit exists, these two things should be equal. So this must be equal to partial derivative of u with respect to x plus I partial derivative of v with respect to x. So f prime is equal to partial derivative of u with respect to x plus I partial derivative of v with respect to x. That's one way to write this down. And the second way is minus I partial derivative of u with respect to y plus partial derivative of v with respect to y. Okay, great. So if these two quantities are, both of them are equal to f prime, they must be equal. If two complex numbers are equal, their real parts must be equal and their imaginary parts must be equal. So the real part here is this one, And the real part here is this one. So they must be equal. So partial derivative of u with respect to x must be equal to partial derivative of v with respect to y. And here the imaginary part is partial derivative of v with respect to x. Here the imaginary part is minus, there's a minus sign here, minus partial derivative of u with respect to y. So these are the Cauchy-Riemann equations. So we learned being complex differentiable implies being holomorphic. Okay, now what about converse? Does being holomorphic implies being complex differentiable? Essentially, yes. So there are some details one should be careful about. So if you have a function f equals u plus iv, where u and v satisfy the Cauchy-Riemann equations, and something else to be careful about, it's important to have this assumption that the partial derivatives of u and v with respect to x and y are themselves as the derivatives, as functions, are continuous. If we have both of these, this would imply f is complex differentiable. This is what I'm going to leave to you. This is not very challenging, but it's a very good exercise. And it's important to know if you don't have this extra assumption that partial derivatives are continuous, in fact, you can cook up counterexamples. There are examples where u and v satisfy Cauchy-Riemann equations, but u plus iv is not complex differentiable. And it has to do with the fact that partial derivatives of u and v are not continuous. So this is important to have this assumption. Okay, so now we learn complex differentiable implies being holomorphic, and I left that to you that being holomorphic implies complex differentiable. So in the next part, we are going to discover what does it mean to be analytic and how is it related to the other two notions, right? As the closing question, I'd like you to answer this question. Do you know who wrote the Cauchy-Riemann equations first? Cauchy, Riemann, someone else?